Hello, it's Miss Adams from Flamingo Math. Today in Lesson 8, we're going to talk about rational functions and zeros. We want to fine-tune our techniques for analyzing the graph of a rational function. So let's revisit the procedure that we developed in our last lesson, and we want to expand on finding zeros and solving rational inequalities. First of all, let's think about the characteristics. If r of x is a rational function and the numerator is n of x, the denominator is d of x, and let's say they have no common factors, then the rational function is said to be in lowest terms, and we know that these characteristics will apply. First of all, we know that there are no zeros where the numerator is 0, but not the denominator 0. And we know that r of x is undefined when the denominator is 0. So these are two important facts. We're going to have the numerator 0, that's going to be zeros of the function. The denominator is 0, we're going to find out that that is going to be a vertical asymptote. In the next lesson, we'll find out and discuss what happens if there is a common factor. So let's take a look at example 1. We want to use the procedure above to find the zeros of the rational function. The first thing that we want to do is to factor the numerator. So if you think about factors of 12, that would add to be 7, I believe. 4 times 3 would equal 12, and 4 plus 3 would give us that middle term of 7x when we distribute. The denominator is the difference of two squares, and factoring the difference of two squares looks like x plus 1 and x minus 1. So the zeros come from the numerator. They are what makes those two factors zeros. Our zeros would be at x equals -4 and x equals -3. These are the zeros or the x-intercepts of the function. And then to talk about the end behavior and use limit notation, we know that, got the wrong pointer there. We know that the limit as x approaches -infinity for r of x. Now, what was the rule? Got to think about this. We had the rule where the numerator and the denominator had the same powers. So x to the second over x to the second. If the powers were equal, then you had a horizontal asymptote at y equals 1. So our graph is going to head to 1 on the left and 1 on the right. So these are the rules from the last lesson for the end behavior. We know the zeros and we know the end behavior. Going on to example 2, this time we've got the graph of the function, and we're going to analyze looking at the graph. So using the rule of 4, you can observe that we have a 0 at x equals -3. So that's this point right here. We have a horizontal asymptote. It appears that the graph is heading to the left and the right at extreme behaviors or unbounded behaviors. The graph is heading to 1. Using limit notation to express that behavior, the limit as x approaches -infinity for our function y is going to 1, and the limit at the right as x approaches +infinity on our graph is also heading to 1. What is the factor of the numerator? Well, the factor of the numerator comes from when x is -3, so the factor would be x plus 3. That's what causes the 0. So graphically, we can analyze the function and come to some conclusions. The rest of the lesson is about solving rational inequalities. We have to locate the zeros and we have to locate undefined values. We can use a procedural approach to solve rational inequalities. Remember, when the function is above or greater than 0, that means the graph of f is above the x-axis. And when the function is less than 0, that's going to tell us the graph lies below the x-axis. I'm not going to read these 7 steps. I'm just going to model them for you in our examples. So first thing we want to do is we want to isolate the inequality so that 0 is on the right. And in this case, we've got r of x is greater than 0. So x minus 2 over x squared minus 9. I'm going to factor that as we go along. We want that to be greater than or equal to 0. So we isolated the inequality. We want the left side of the inequality to be a single rational function. It is. We want it factored so that we can say when is x minus 2 is 0 when x is 2, and the denominator is 0 when x is negative 3 or 3. So I'm calling these my critical values of that inequality. And we're going to make a number line, and we're going to test values in between negative 3, positive 2, and positive 3. So those are our critical numbers. And like we did with the other inequality, let's say we test a number, say negative 4. So if I put a negative 4 here and a negative 4 here, and think about all the math, a negative 4 minus minus 2 is a negative number. And negative 4 squared is 16, and 16 minus 9 is going to be a positive number. So testing negative 4, that area is a negative value. Does that make sense to you? Hope so. And then moving to the next section, we know that x is negative 3. This number is undefined because it was division by 0. And this number was undefined because it was in the denominator. But 2 is in the numerator, so 2 is a 0 of the function. Now let's think about this section in here. Can we test 0 in here? So if you put 0 for x and 0 for x squared, you've got a negative divided by a negative. That forces that section to be above the x-axis. And then between 2 and 3, we could do that by using the graph and not substituting, because take a look over here. What we're finding out is absolutely true. This section was below the x-axis. This section is above the x-axis. And then between 2 and 3, this section is below the x-axis. And then the last section is above the x-axis. So where is our statement true that r of x is above the x-axis or it's positive? It looks like it's true. Whoop, got the wrong color there. Let's get yellow. It looks like it's true in here and that it's true in here. So we could write that statement by saying r of x is greater than or equal to 0 on the interval from negative 3 to 2, and it's equal to, so we want to close it at 2, and it's also true from 3 to infinity. Now I want you to notice that I circled this because that's a vertical asymptote, and 3 is also a vertical asymptote. We can't have division by 0, so it would never be equal there. It has to be greater than or equal So we had open parentheses at -3 and at +3, but it was exactly 0 at 2, so that closed the bracket there. So graphically or numerically, we can analyze rational inequalities. This one, solving algebraically, again, we want to have a number line, and we're looking for areas where it's true. So I'm looking at the zeros would be at 1, 2, and 4, +1, +2, +4. Those are zeros of the function, of the inequality. And we want to solve that inequality. So if you substitute some number in this region here, this section over here, if we substitute 0, we've got -1 times -2 times -4. So that's a negative times a negative times a negative. That section is going to be negative or below the axis. Following through in this next section, if you had 1.5, this would be a positive number, a negative number, and a negative number. So a positive times a negative is a positive. So this section would be positive. And we're looking for where it's below the axis. So right here we know that this section is true and this section is false. Between 2 and 4, let's try a 3. So if we have a 3 here, a 3 here, and a 3 here, that's going to produce a negative value. This section is true. And then greater than 4, if we had a 5 here, a 5 here, and a 5 here, that's going to produce a positive result. So this section is false. And thinking about the truth, we want the truth where the rational or where the polynomial function is less than or equal to 0. What happens with the zeros? It's got to be equal to, so this would be true, this would be true, and this would be true. And then transferring that to write a symbolic statement for the answer from -infinity to 1, including 1, and then again between 2 and 4 inclusively, that inequality statement is true. And part B, we've got a little bit of a problem because we want to isolate that term. So to isolate the 2 on the other side, x plus 1 divided by x minus 3, and we want to subtract 2, we need a common denominator of x minus 3. So we'll use a well-chosen 1 in that form and say that's less than or equal to 0. So if we distribute 2x to those two terms, I believe we're going to end up with 7 minus x in the numerator because we've got x plus 1 minus 2x plus 6. So there's 7, and 1x minus 2x is negative x. So I did do that in my head, okay. The denominator is going to be x minus 3, and we've got less than or equal to 0. So following that same procedural approach, the numerator is 0 at 7. The denominator is 0 at 3, but the denominator is a vertical asymptote. It can't be included. 7 is a 0. It can be included. And we want to test some numbers like 0, 4, and 8. If we test those numbers, 0 is going to give us a positive in the numerator divided by a negative. So this is all going to be a positive divided by a negative. This is going to be below the axis, so this is a true section in our solution set. This part is part of our answer. In the next section, if you substitute a 4, we've got a positive in the numerator divided by a positive, and that's above the axis, so that's a false area. And substituting 8 into our terms, both here and here, 7 minus 8, that's going to give us a negative in the numerator and a positive in the denominator. This section is also true. So writing out our solution set to the inequality from negative infinity to 3, do not include 3, and include 7 and go to infinity. So this is our solution set. Part C, what's going on? We've got everything is factored and isolated. So we're looking at 2 is a vertical asymptote. Negative 2 is a 0. This is a do not exist vertical asymptote. 3 is a 0. Got that from the numerator. So we could include greater than or equal to. We wouldn't include 2. We can include negative 2. I'm going to test numbers like negative 3, 0. See, we'd need 2.5, and 4. And to save time, I found that this was a positive area. This was a positive area. This area was below the axis, and this area was above the axis. So where are we true? We're true through here up to and including here. So we're true all the way through there, and then we're true from 3 to infinity. Our solution set would be from negative infinity all the way to positive 2. Do not include positive 2. Include 3, and everything after 3. So our solution set looks like that. Example 5 is our last example. The graph is shown at right, and we're going to use the graph to solve the following inequalities. So where is the function less than 0? So the function is less than 0 or equal to 0 from negative 3 to negative 1, and from 2 to 3. So shading that helped me out. From negative 3 to negative 1, and it includes negative 1, and it also includes 2, and stops at 3. That's a vertical asymptote. Okay, second thing, we're going to say, where is h of x greater than or equal to 2? Well, it's not equal to 2 anywhere, since 2 is a horizontal asymptote right through here. You can see that horizontal asymptote. So where is it greater than? From negative infinity to negative 3. Don't count negative 3. And then on the other side of the other vertical asymptote at 3, all the way to infinity. And last but not least, on C, where is h of x above the x-axis but not equal to the x-axis? So that's going to happen from negative infinity over to negative 3, in between negative 1 and 2, right in here. Don't count those zeros. And then after 3. So we could write that in a nice, concise notation: negative infinity to negative 3, negative 1 to 2, but it's not equal to, so we're not going to bracket 1 and 2. And then finally from 3 to infinity. And I believe that's the end of this lesson here. That was fairly straightforward. See you next time.